I've been talking about trends in the periodic table. And the first trend that we looked at, oh, I got to start up so I get my little, can mark down here, where is Keynote? There it is. I also noticed I'm hearing a lot fewer, I think that's the grammatically correct word to say, a lot fewer ambulances like I used to about a month ago. It's just because I just hear one now and it reminded me. Anyway, the trends that we looked at, number one was atomic radius, which is basically the size of atoms. And the trend for that was that they increase going down the group and they increase, I guess, going from right to left, or you can say they decrease going from left to right, depending on how you want to remember it. And then the second one I looked at was ionization energy. And just to remind you, that is the energy required to remove an electron from a neutral atom. And ionization energy increases going from left to right, which means it becomes more difficult to remove an electron. I like to think of ionization energy in the first one I'm going to talk about after this, electron affinity, as the ease or difficulty with which you either remove or add an electron. And that difficulty is measured by the energy that's required. So if more energy is required, it's more difficult to remove an electron from a neutral atom. And let's see, and then of course, the hardest ones are going to be at the top, because those are going to be the atoms that, first of all, want electrons. They don't want to get rid of them. They want an extra one because they're on the right-hand side of the periodic table. And also the ones at the top, because those are the energy levels that are the closest to the nucleus. So the easiest ones to remove electrons from are down here in the bottom left, because they want to get rid of electrons to be like the noble gases in group 18. And also because the electron that you're going to remove is going to be further away from the nucleus if you're down at the bottom of the periodic table. Now, having said that, there is first, second, third, etc. ionization energies. So your first ionization energy is removing an electron from a neutral atom, and then you get a positive ion after that. You have a second ionization energy, which would be removing an electron from that positive ion. Now, depending on where you start, the first and second ionization energies can be either higher or lower than the other one. So I think I use the example of sodium, which is all the way on the left-hand side of the periodic table. The first ionization energy is going to be ridiculously low. It's going to be super easy to remove an electron from sodium. But as soon as you remove that first electron, it becomes a sodium ion. It has the same electron configuration as neon. And so the second ionization energy for sodium is going to be ridiculously high. It's going to be near impossible to remove a second electron from a positive sodium ion. If you look at something on the right-hand side of the periodic table, first ionization energy is going to be high, second ionization energy is going to be high, third ionization is going to be high, because you're just basically moving it backward, or you're moving it to the left. And when I say you're moving it, I mean the electron configuration is going to change by one element to the left as you move. So it's not until you like remove 6 or 7 electrons that it becomes very easy to remove the other ones. Okay, so having said that, to review last week, the third trend I want to talk about is electron affinity. This is basically going to be the same thing as ionization energy, but we're adding an electron to a neutral atom. The word affinity, just as an English language word, just means like an attraction for or a tendency to like. If you have, or even just like an interest. I'm going to say, like, if you have an affinity for science, that means that you're interested in science. If you have an affinity for art, maybe you're good at drawing and you like doing those things. So it's kind of like, an interest in. So neutral atoms can also gain electrons. So electron affinity is the energy change that occurs when an electron is acquired by a neutral atom. Now, here's where it's going to get confusing because atoms release energy when they get an electron. When I talked about ionization energy, I talked about an atom needs to gain energy before it releases an electron. This is the opposite. So when you give an atom an electron, it releases energy. So we can use the same kind of variables to represent everything. A is a neutral atom. E minus is an electron. So if you add an electron to a neutral atom, you get an anion and energy is released. Okay. When in this statement here is true for every situation, like in science in general. If energy is released, it's always represented by a negative number, which seems kind of against logic, but that's how it is. When energy is being released, that means it's exothermic, even though therm means heat, but the energy is often released as heat. When it's being released, we use a negative number to represent that quantity. Now, just to make a distinction, for ionization energy, because I want to make sure that we don't get confused. Ionization energy, you have a neutral atom, you give it energy, and it releases an electron to become positive. I don't know if I've used this abbreviation before, but I learned this from my chemistry teacher. It's just an abbreviation for energy, so I don't have to write out like the other 3 letters. I can be extremely lazy sometimes. And if you don't get it, you just say the letters NRG, energy. Okay, just to be clear. So this is an indication of how difficult it is for an atom to release an electron. If this energy is low, then it's easy to release an electron. If it's high, it's hard. EASE. Oof, I can tell it's a Monday morning. For electron affinity, because the energy is being released, it's actually the opposite. So if the energy that is released is low, that means that it's hard to gain an electron. And if it's high, it means that that atom really, really, really wants an electron. So I just want to make sure that I make that distinction. Okay, so they're opposite. The reason why they're opposite is because the energy is on opposite sides of the chemical equation. So the meaning is opposite. Okay. So there are some atoms that really, really don't want an electron. And instead of releasing energy, you actually have to force them to take the electron by adding energy. So that would be represented by having energy on the left-hand side, on the reactant side of the chemical equation, because not only do they not release energy, but you have to actually force them by adding energy. Now, again, this next statement is true. Oops, I can't do that. That last statement is true for like all across science, because we're talking about here the energy being a reactant, being absorbed. That's an endothermic situation, and the number when you have energy being absorbed is represented by a positive number. We go into more detail about why that is next year when we study thermodynamics. If this is the case, so for example, a noble gas, right? Noble gas is a great example to use both for ionization energy and electron affinity, because noble gases don't want any change at all. They're like, nah, I'm good, bro. Like I've got the perfect number of electrons. My outer level is full. I don't want to lose an electron. I don't want to gain an electron. So if you take neon, for example, and you add energy to neon, thereby forcing it to take an extra electron, as soon as that energy is gone, it's going to release that electron again. It's like, yeah, no, I don't really want that. It's like being stuck with somebody you really don't like. And the first chance you get, you're like, go away. So looking at period trends, again, period trends, we're going from left to right. Now you can see the shades of red get darker as you go towards the right-hand side. It's not like a very clear pattern, but you do see that the halogens, which again is group 17, these are the halogens, they have the highest electron affinity because they are in group 17. They are exactly 1 electron away from being quote unquote perfect when it comes to electron configuration, like the noble gases. So they seriously want that electron. They're going to have the highest electron affinity. So we can say from going from left to right, the electron affinity generally increases as you go across the period. Now, just like group 1 that I talked about last week have the lowest ionization energy, meaning they really want to get rid of an electron that makes them as reactive as they are. The same exact reason can be applied with reference to electron affinity, meaning the halogens have the highest electron affinity, meaning they really want an electron for their neutral atom. And that is the reason for their reactivity. So like I've said before, I think when you get a group 1 metal together with a halogen, whoo boy, that's a party. What about going down a group? See if we can figure this out. If you go down a group, do you think it's going to be easier to add an electron to a neutral atom, or do you think it's going to be harder? So we apply the same logic that we applied to the other trends, meaning what is changing if you are within the same group, say group 1 or group 17, which you just pick a group. As you're going down the group on the periodic table, what is changing? And the answer is the energy level to which you are adding the electron. The further you go down the group, the higher the energy level of the orbital that is accepting the electron, and therefore the further away from the nucleus. So the trends for electron affinities, as I said on this slide, it's not an extremely regular pattern like you see with atomic radius and ionization energy. It's a little bit more spotty, I guess you could say. But the general rule for the group trend is that electrons are added with a greater difficulty as you go down a group. And exactly for the reason I just talked about. The energy level that you're adding the electron to is further away from the nucleus. So you've got 2 problems as you get farther away from the nucleus. One, you have a lot more electrons, so there's a lot more negative charge hovering around, and negative charges repel each other. And you have this what's called electron shielding, meaning you've got more levels of inner shell electrons that are how to call it, like, I guess just shielding, because that's what they call it, electron shielding, are shielding the single electron you're trying to add from the nucleus, which it has a positive charge, obviously. So in general, this is why we talk about generalities. In general, as you go from left to right, electron affinity increases, because remember, affinity means that you are interested, you like it, you want it, kind of thing. So as you go from left to right, the elements on the right-hand side want electrons more than the elements on the left-hand side. Going down a group, it decreases. So I should Yeah, so greater difficulty means abbreviating electron affinity with EA sports. It decreases. That's what that means. Decreases going down the group. I don't want to do that because I use arrows in different ways, but so that's the general rule. Electron affinity increases from left to right, decreases from top to bottom. And again, the two competing factors are one, a slight increase in nuclear charge going down a group, which you would think would increase the electron affinity, because remember, as you go down a group, your nuclear charge is increasing by a lot. But counteracting that is the increasing radius, which means your atom is getting bigger. And like I said before, you've got more electron shielding, and the electron that you're adding is further away from the nucleus. So these two things are contradictory to each other. But it turns out that number two wins in the end. So it becomes more difficult to add electrons. And again, with this graph, which I should just remove because I don't think it's very useful at all. If you look at this and it speaks to you and it makes electron affinity make sense to you, then by all means use it. To me, it just kind of looks like almost like an EKG, like those heart monitor things that you see on the medical shows when it's like beep when somebody's dead. Like just before that happens, this is what it looks like to me. But again, we all, our brains all work differently. So sometimes what doesn't work for me, somebody is like, oh my gosh, that makes everything make sense all of a sudden. So up to you. I guess that's why I keep it in there. All right, and just like in ionization energy, where we can remove electrons from positive ions, we can actually add electrons to negative ions. And the same kind of logic, is going to apply. So let me exit here for a second and just use the periodic table for a sec. If I can find it. There it is. And then let me stop this and go back and share that. Okay. So everybody sees a periodic table to me?
Yes.
Yeah, all right, cool. Just making sure I didn't share the wrong screen because I've got like 6 screens up. All right, so electron affinity. We've already established that group 17 here has the highest electron affinity. Now, of these, fluorine is going to have the highest affinity because number one, the electron that you're adding is only in energy level 2, which is very close to the nucleus. And also it's 1 electron away from being like neon. So it's like the most desperate element for an electron. However, once you add that electron to fluorine and it becomes a fluoride ion, so it would be F-1, and it has the configuration of neon, it is not going to want another electron. So it becomes extremely difficult to add a second electron to the fluorine atom, because for the same reasons that I talked about last week with ionization energies, so even though when the neutral fluorine, gotta make sure I use the right word, when the neutral fluorine atom is given an electron, it's going to release a ton of energy. But once it has the configuration of neon, so we're talking about F-, then it's going to go into that other category of needing to add energy to it to force it to accept a second electron. So I just wanted to make that clear by showing the periodic table. At the same time, if we go to oxygen, will be another good example. The energy that's released from oxygen when you add the first electron to the neutral oxygen atom is going to be like, meh, okay, like it wants electrons, and like 1 electron, it's like, okay, thanks, but like, can you give me more? The second electron that is added to an O- ion is going to release huge amounts of money, I wish, huge amounts of energy, because the second electron is what's going to kick it up here to the configuration of neon. So again, with the periodic table, I was just, there's a guy I follow on Twitter who's like this politician guy, but he's been on, I don't know if you know the trivia show Jeopardy, where there's like a statement and then you have to answer, like you have to, how is it? You have to say the question that the statement answers. Anyway, I'm just completely screwing that up. There's a guy I follow on Twitter that had a very funny story about when he was in chemistry, and he thought he would try to trick his chemistry teacher and say like, and ask him, what's the atomic mass of palladium? And he thought like, you know, he'd be really first try to test his teacher to see how much chemistry knowledge he actually had. But two, we thought it was like a gotcha, like, haha, see, you don't know. And his teacher was like, I don't know, Tom, like, why don't you look at the periodic table back there and tell me? So that's kind of the same thing here, where I'm like, I would rather teach you about the periodic table, what it is, how it's set up, what information we can gain from it, instead of like a lot of times students in the very beginning will ask me like, do we have to memorize it? I'm like, for what? What possible use could memorizing the periodic table give you besides a party trick, I guess? Like if you want to look super smart and like prattle off the elements of the periodic table, I don't care if you memorize it. It's a tool like a calculator is. I also don't understand why you've got like higher level maths classes, at least here in Thailand, where it's like you're not allowed to use a calculator. I'm like, why? Are we testing our like mental math skills? Or do you want us to do calculus? Like pick one, you know? So anyway, that's just my philosophy on it anyway. So if any of you guys want to try to like trick me and say, what's the atomic mass of blah, 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 I'm gonna be like, I don't know, go look it up. Cause like, that's what it's there for. Right. So I'm going to kind of like go through there. Cause I just explained it. It really just depends on where in the periodic table the element is placed. And based on that, you'd have to make a decision on what the affinity is going to do as you add more electrons to the negative ion. So let's do an example. Chlorine. We have chlorine that has a 3p5 configuration. So when it gains an electron, it's going to release tons of energy because it will be just like argon. It will become 3p6. And we know that P can hold a maximum of 6 electrons. So that would make the chloride ion. So when you have ions that become negative, like this is called chlorine. This is called chloride. Oh, I can write properly. There we go. Chloride. So any negative ion, you have to change the ending to IDE, indicating that it's an ion. For positive ions, for some unknown reason, oh, probably there is a reason, I just don't know what it is. Whether you have a sodium atom or a sodium ion, the name is the same. Don't really know why they didn't change it, but maybe I'll look that up after class if I remember. All right, if we have the chloride ion, adding a second electron is so hard that you never see Cl -2. You just don't see it. It doesn't exist. I mean, it could exist probably for like a millisecond, but again, you're going to have to use energy to force it to take the electron. And as soon as that energy is gone, it's going to kick the electron out again. The next property to look at is going to be a little bit different in the way that we approach this. We're not really going to look necessarily at period and group trends, although I'll still mention it. What's more important with ionic radii is comparing the radius of the ion to the radius of a neutral atom of that element. So what I mean is, for a cation, remember it's not a cation, it's a cation. For a cation, will a cation be larger or smaller than its atom? And then same for an anion. When a cation is formed, the cation is going to be smaller than the neutral atom. And I can actually explain this if you guys are like super logical, like number thinking kind of people, you can just use straight up math. So let's just take lithium as an example. Let me try to write properly. Okay. So lithium has a atomic number of 3. So that means that it has 3 protons and 3 electrons. Why is that little thing done? I don't know. So for every proton, you have 1 electron. When it becomes a lithium ion, it has lost an electron, but you still have 3 protons, but now you only have 2 electrons. So overall, if you just look at the distribution of positive and negative charges, you have the same amount of positive charge, but you have less negative charge, which means that the positive nucleus is going to have a greater effect on the electrons. So if you think about, because we know positive and negative attract, right? So basically for every proton, you're attracting an electron, if you want to think about it that way. But if you have a lithium ion, you now only have 2 electrons, but they're filling the same pull from 3 protons. So now you've got more than 1 positive per electron. So feeling that attraction. So the electrons get pulled in a little bit closer towards the nucleus. Now, when it comes to going down, oh, I'm not going to talk about that yet. Okay. No, I'm going to talk about that now because I would like to do them while I'm here. Right. So as you go down a group, again, think about the electron that's being removed. So as you go down a group and you are removing an electron to form a positive ion, that electron that's being removed is like really, really far out. So even though the ion gets smaller than the atom, the difference in size is going to be smaller if you're down towards the bottom of the periodic table. So I don't know if what I'm saying is making sense because I feel like I'm not explaining it very well, but the ions that are formed up here are going to be much smaller than their atoms. The ions down here are going to be smaller, yes, but they're going to be less small than the guys up here because the electrons here are very close to the nucleus. Again, it's all about where the electrons are. These guys are all really close to the nucleus. These guys are super far away. So if you remove an electron from here, then it's going to decrease in size a lot, to a greater extent than the ones down here. Oof. Let me go back up to, yeah. All right, now for an anion, we know that anion is negative. When an anion is formed, the anion is always going to be larger than the atom that formed it. And you just reverse the argument that I just made for why a cation is bigger. If you add an electron, so let's go with fluorine, which is number 9. So we have 9 protons and 9 electrons, right? So there's an equal amount of positive to negative, but the fluoride ion still has 9 protons, but now it has 10 electrons. Now, the reason why this results in a larger ion is because of the electrons that you're adding to this, the outer energy level, that's going to have more negative charge, and negative charge repulses or repels negative charge. Negative doesn't like negative. So they're going to push out against each other and they're going to take up a little bit more room. Get rid of that. Okay. So the electron cloud spreads out because you have an increased number of electrons, which means a greater repulsion. All right. Now, basically talking about the periodic table in general, metals form cations and nonmetals form anions. And if you're not sure where the metals and nonmetals start and stop, if you start underneath boron, and it's not exactly the case, but just for now, it just is super easy to remember. Just draw a staircase going down. So starting under boron, just go 1 over, 1 down, over, down, over, down, over, down. And like I said, it's a little bit different when you get around the antimony tellurium area, but just as a general rule, that line separates the metals and the nonmetals. So the nonmetals are in the upper right corner, and everything else to the left of that line is a metal. So all of these guys are going to be positive. And this is why I like this periodic table in general. You see up here, all positive numbers. These all tend to lose electrons to become positive. Later on, you'll find out why there's 4 different charges there, but for now, go back here. Okay. Okay, so if you're going to compare the size of the cations going from left to right are going to decrease in size for the same reason why atoms decrease in size going from left to right. And anions are going to decrease across each period for the elements in groups 15 to 18. And again, remember, I'm limiting it to groups 15 to 18 because those are the groups that form anions. Everything else forms cations. So in general, whether you're a positive or negative ion, your radius decreases from left to right for exactly the same reason that atomic radius decreases from left to right. You have increasing positive charge as you move from left to right, but the electrons are all still in the same energy level, so they're all the same distance away from the nucleus. So as you increase the positive charge in the nucleus, you're going to pull the electrons in closer, making it a smaller substance or thing. I don't know what classifier to use. The outer electrons in the group, the outer electrons in both cations and anions in higher energy levels. Huh? Outer electrons? That statement makes no sense. Oh, no. Yeah, now I get it. The outer electrons in both cations and anions are in higher energy levels as you read down a group. Sometimes using like shortened English even confuses me. So this means that as long as we're staying with ions, whether it's a positive or negative ion, as you go down the group, the size of the ion is going to increase again, just because you're adding energy levels, they're getting further away. So whether you're talking about ionic radius or atomic radius, the group and period trends are the same. So there's nothing new to remember there. And they're the same reasons given as well. But more importantly, you want to be able to compare the size of an ion to its atom. So cations are smaller than their atoms, anions are larger than their ions. And I think the last property or the last trend to look at are valence electrons. These are electrons that are available to participate in forming bonds, whether the electrons are going to be lost, gained, or shared. Now, if electrons are lost or gained, they're going to participate in an ionic bond. If the electrons are going to be shared, it's a covalent bond. And I'm going to talk more about that in chapter 6, which is like a really big, heavy, complicated chapter. Valence electrons are, I would say, almost always located in incomplete main energy levels. I can't honestly think of any example where you would have a complete main energy level and have valence electrons, because that would make it a noble gas, and noble gases just don't react. So here's a really easy table to figure out valency as you go through the periodic table. So group 1, their group configuration was NS1. That 1 electron is the valence electron. And then I want you to notice when you add the p. When you add the p orbital, you start to add both the s and the p electrons together because they're all in the same energy level. For example, if n equals 3, remember n is the principal quantum number. quantum number, which is the same as period number. Okay, so if n equals 3, then for this one, it would be 3s2, 3p1. Valence electrons are the electrons that are in the highest energy level. So you would include both the s electrons and the p electrons. And again, what I mentioned, I think probably a couple weeks ago now, when you get to groups 13 to 18, the number of valence electrons is the group number minus 10. So group 13 has 3, 14, 4, blah, 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 like that. Okay. So if I have 3s2, 3p1, that means that I had 2p6, 2s2, and 1s2. That makes all of these electrons in blue here, the 1s2, 2s2, 2p6, those 10 electrons, those are what's called inner shell. And I think I've mentioned it before, but just in case, inner shell electrons. And those belong to the that atom by itself. They are not available to participate in bonding. Oh, no, I've completely forgot about one of the most important, holy crap, I can't believe I forgot. One of the most important group trends, you're going to hear about this property in future years, and especially in the next chapter as well, but we're going to talk about electronegativity a lot. And I do know from experience that this is one of the terms that there's no Thai term for it. So it's literally just translated into Thai, electronegativity. So if you ever see that, this is what it's talking about. I like to abbreviate it EN. Again, I'm lazy and I like to make my life as simple as possible. Now, electronegativity is going to be the same idea as electron affinity. However, it's going to be how much an atom likes electrons or attracts electrons when they're in compounds. And that is what distinguishes electronegativity from electron affinity. Electron affinity is how much a neutral atom all by itself, how much does that atom want an electron? Electronegativity is when you have a compound that has more than one atom in it. How much does each atom attract the electrons that are in that compound, particularly with covalent bonds? Because these are when electrons are being shared. And you've already studied electronegativity. You just didn't know what it was called. And it was when I talked about this guy at the very beginning of time. When you have water, the electrons are shared between oxygen and hydrogen, but they are not shared equally. Does anybody remember what property results from that? It's the one property, if I ever, and I will, if I ever ask you what is unique about water, what is so special about water, why would water do this when this compound doesn't do that? There is one thing I want you to remember. And I'm always successful at having my students remember at least this one thing, is because the electrons between the oxygen and hydrogen are shared unequally, it means that the electrons spend most of their time around oxygen and less time around hydrogen, which makes the oxygen slightly negative and it makes the hydrogens slightly positive. Now that goes, it's separate for each bond. You look at each bond separately, but because they're exactly the same between oxygen and hydrogen, they have the same result. What happens is if you divide the water molecule down the middle, you will see between the top half and the bottom half, you have two opposite sides or poles. So sharing electrons unequally results in polarity. And that is the one thing, if you learn nothing from me in 3 years, you will at least walk away with anytime anybody asks you anything about water, the first thing that's going to pop into your head is polarity. That's it. Because all of the things that we talk about, not just in chemistry, but also especially biology, because we are made mostly of water. Water is required for life. And so it has all of these amazing properties, not the least of which is temperature moderation. So if you think about the fact that water stays a liquid from 0 degrees all the way up to 100 degrees, that is an amazing property to have as a liquid. That's a huge temperature range. And the reason is when you have other water molecules around, of course, all the hydrogens are slightly negative or slightly positive, all the oxygens are slightly negative, and so you end up getting this hydrogen bonding. So between 0 and 100 degrees Celsius, all of that energy that's being added is going towards breaking the hydrogen bonds and freeing each water molecule from each other. And then it's able, finally, when all of the hydrogen bonds are broken, then it will finally start to boil, only at 100. This is very, very useful if you're made mostly of water. That means you can go outside. If it's like 45 degrees outside, you're not 45 degrees. Okay, so again, in many compounds, a negative charge is centered around one atom more than another. And like I just finished explaining, an uneven distribution of charge has an effect on a compound's property. So it is useful to have a measurement of how strongly one atom attracts the electron of another atom. If you guys don't know who this is, oh, stop. I didn't want you to talk right away. If you don't know who this is, wait. If you don't know who this is, his name is Hank Green, I think.
Oh my gosh, Hank Green.
Yeah. He runs,
Oh my God.
he runs a channel, or there's a few channels probably, but the one that I really like is Crash Course. There's Crash Course Chemistry, Crash Course Biology, whatever, physics. I think they do ecology. I don't know if they have history, psychology. I don't know, lots of different subjects. He's one of the best, in my opinion, one of the best YouTubers as far as like explaining things. He does talk super fast. So I don't like, if you guys can understand me, you can understand him anyway, because I also talk fast. Must be an American thing. He covers every single topic that I teach. So if for some reason the way that I'm explaining things doesn't work for you, or like even if it's a particular topic, you're like, I don't get it, you can always go to YouTube and look at Crash Course, whatever, biochem, blah, blah, blah. They've got every single topic that I teach. And he's funny.
Electronegativity is usually thought of as how much an element wants electrons around it, but I think it's more about how much electrons want to be near that element. If electrons were 13-year-old girls, fluorine would be Niall Horan. They'll do anything just to be near it. Why? Some simple periodic trends. Electronegativity increases from left to right because there are more protons in the atoms, and more protons means more boys in the band. Meanwhile, it decreases as you move from top to bottom because as the crowd of electrons gets bigger, they start to shield each other from the effects of the protons. What I'm trying to say is that electrons are hipsters. If a bunch of other electrons are into that thing, they're less interested. Now, there are a number of other factors here, but just like the relationship between tweens and their latest boy band fixation, it's complicated and weird, and you probably don't want to think too much about it. But in this nice little map, you can see that the trend is pretty clear. The upper right is where all the superstars of electro fame are. Oxygen, nitrogen, fluorine, chlorine, and bromine are basically the one direction of the periodic table. So for
that's actually a pretty brilliant analogy to use. That like the members of a boy band or girl band are the electronegative elements, and then the fans are electrons. So if you've got, like, oh, I forgot what he said, but anyway, the more fans you have, then the less effect electronegativity has, because you're not, like, I guess, as close, you know what I mean? So electronegativity is the measure of an ability of an atom to attract electrons. You can, like he said in the beginning, you can also think about it as like, how much do electrons like that particular element, but it's really about the element and how well it attracts electrons when it's in a compound. Again, this in a chemical compound, that is what distinguishes electronegativity from electron affinity. That's the only difference. Otherwise, the concept is exactly the same. Now, fluorine is the most negative, the most electronegative element, and it's been randomly assigned a value of 4. I don't know why 4. I'm sure there's a reason, because usually scientists don't just make crap up. All of the other values of electronegativity are calculated in relation to F. So fluorine is used as the standard. Now, how well other atoms can attract electrons when it's in a compound compared with fluorine, that's how you come up with all of these values. So without even really needing to go into like period and group trends, I have one rule for you, which is the closer it is to fluorine, the higher its electronegativity is. So if you're super close to fluorine, you're going to have a very high electronegativity. If you're far away, not so much, because fluorine is at the top right-hand corner of the periodic table. Electronegativities are going to increase going from left to right. Of course, there are exceptions. But for the most part, the alkali and alkaline earth metals, which are group 1 and group 2, are the least electronegative. So in compounds, their atoms have a low attraction for electrons. So here's a nice little kind of 3D bar graph, which shows you that all the elements in the top right corner have the highest electronegativity. Nitrogen, oxygen, and fluorine are the most electronegative, followed closely by chlorine. So if you go down the group, electronegativities are going to decrease or possibly stay the same, which you can kind of see in that group here and here, that the kind of the height of the column doesn't look like it changes at all. Now, you do have these values, and again, you don't have to remember the values. The only number that maybe you have to remember is that fluorine is 4. I think that would be the only thing that's oh crap.
Wait, we're over time. 10 minutes.
Yeah. Okay. Thanks. I know. Oh, it's 11:10. Oh, I thought it was 11:20.
Yeah.
Oh my God. Sorry. Okay.
Oops.
Bye.
I'll see you. See you.
Thanks.
See you.
Thanks for
Bye-bye.
calling.